So now on to our second speaker, Distinguished Professor Joe Mitchell. Here to introduce him is Alan Tucker. He's a SUNY Distinguished Teaching Professor in the Department of Applied Mathematics and Statistics. He's a fellow of the American Mathematical Society and of the American Association for the Advancement of Science. He's the editor-in-chief of Applied Mathematical Letters. Alan began his career doing research in graph theory and combinatorial algorithms. More recently has become increasingly involved in K-12 mathematics instruction, including directing large regional and national NSF initiatives to improve collegiate and K-12 math instruction. And I talked before about Patricia being an amazing mentor. Alan is one of just the most dedicated teachers. When Alan talks to you about teaching, you see him light up. He's like a young boy when he talks about it, and I just find it so inspiring. And I think as we think about who we are as a research university and the importance of the teaching mission within that, he is just a tremendous model for all of us. So, Alan.
It's a great pleasure to be introducing Joe Mitchell. He's Fry Family Foundation Professor and SUNY's Distinguished Professor in the Department of Applied Mathematics and Statistics. He's also been our department chair since 2014. He holds MS and BS degrees from Carnegie Mellon, where he happened to have been valedictorian of his class, and has a PhD from Stanford. Joe taught for a while at Cornell before he came here. Joe's various research recognitions include a fellow of the ACM, that's the Association of Computing Machinery, the Computer Science Society, an NSF Presidential Young Investigator Award, Fulbright Scholar, and most importantly, the 2010 Gödel Prize winner. This is an international award given every 4 years for outstanding contribution to the field of theoretical computer science. Joe has also been recognized with teaching awards everywhere he's been, including at Cornell in 1990, the best teacher in the College of Engineering at Cornell, among over 300 faculty. And here he has a SUNY Chancellor's Award for Excellence in Teaching. His research is broadly in the area of algorithms, particularly computational geometry. Joe has served for many years on the Computational Geometry Community's Advisory Committee, the steering committee, often as chair, which gives advice to NSF and other agencies about directions for funding NSF and other research in computational geometry. His interests include optimization problems, approximation algorithms, geometric networks. He's worked on applications of algorithms to problems in robotics, transportation, vehicle routing, sensor networks, machine learning, computer graphics, manufacturing, geographic information systems, and computer vision. And when I say applications, I do not mean research papers about this thing, but extensive industrial and governmental consulting. As one example, he has been a leading academic researcher in developing algorithms for NASA and the Federal Aviation Administration to support free flight, where each pilot charts their own flight path, replacing the rigid system of air traffic corridors we have now. Much of this research has been authored jointly with his spouse, Esty Arkin, Professor of Applied Math and Statistics. And I should say personally, I have known Joe since 1983, when he was a graduate student at the Stanford Operations Research Department, and I was a visiting professor. Let us welcome Joe. Thank you.
Thank you very much, Alan, and thank you for the invitation to speak here. I wouldn't be here at Stony Brook if not for Alan Tucker. So thank you very much for that kind introduction. So I study algorithms, and especially algorithms involving geometric data. So I'm going to try to give you a perspective about algorithms and the future of the field of algorithms from the perspective of computational geometry. So first of all, what is an algorithm? An algorithm's a recipe. I took a picture of some chocolate chips. Any kind of recipe to do something, like assemble IKEA furniture, a flow chart for the friendship algorithm, or code. So often people associate algorithms with the computer code, but an algorithm is a higher level concept. It's not just the computer code that might implement an algorithm. So algorithms are everywhere. They're prominent in our everyday life. You can't escape them. I suspect that none of us are escaping an algorithm in the next 30 minutes. We learn them in grade school, as we learn, perhaps, these days, how to do such things as long division, arithmetic operations. Maybe you even learned Euclid's algorithm at some point. But we certainly use them when we navigate. We use them when we search. Everybody's doing searching, and one could claim that Google is founded on an algorithm, a PageRank algorithm that was incredibly successful. Compression of our data, encryption of our data, ranking systems and recommendations that we get from Amazon or anywhere else. Sorting, navigation, all of these. And of course, algorithms sometimes shows up in the media these days as sort of a bad word. It gets a bit of a bad rap because there's the adverse effects of algorithms that might be influencing our buying habits and many other aspects of our life. How do we assess an algorithm? How good is an algorithm? So I work in the field of analysis of algorithms, and we worry about the running time and other metrics that we can measure mathematically about algorithms. So in our field, little n has a special meaning. It means the size of the input. How many numbers, how many polygons, how many entities are in the database. And the thing is, n is getting really, really big now for most problems that we care about. So the running time, we analyze it mathematically. We speak about this so-called big O notation, order n. It grows linearly with the size of n, or n log n, n squared, 2 to the n. That's exponential time. That's a rather slow algorithm. So we look for efficient algorithms. We also look for algorithms that don't use too much memory, because often that's the limiting resource. How much memory do you need in your computer to be able to deal with the number n, the size of the input? Cache and I/O efficiency is also very important because you might be paging data off disk, et cetera. Simplicity is a big one. Make the algorithm simple enough that it can be implemented, analyzed, et cetera. I work a lot in optimization algorithms. You try to optimize, minimize, or maximize some objective function. And then we speak about how close to optimal you are. I work in approximation algorithms, and what's the factor? Energy consumption is a big one now, because as we're learning, our AI algorithms are consuming more and more, a higher percentage of the total electricity in the grid. And fairness of algorithms is prominent today. Now, about 20 years ago, at the beginning, near the beginning of this century, I had the honor of hosting a distinguished lecturer in computer science, Bernard Chazelle, one of the founders of my field of algorithms, from Princeton. And he gave a very influential talk that sticks with me today. And here I reproduced the abstract from it. The algorithm is coming, get ready. He's an advocate for algorithms in science. And his contention is that this is the century of the algorithm. The algorithms will be as prominent in this century as other areas of science, equations, and the development of, say, quantum mechanics was in the 20th century. So I work in a special area of algorithms most of the time, computational geometry. What is computational geometry? This statement comes from the class that I teach. I taught this morning. I teach both undergraduate and graduate computational geometry algorithms. And now, actually, it's become prominent enough that we have the largest cohort of computational geometry students in the country, and quite possibly in the world. More students study computational geometry at Stony Brook than anywhere else. So we learn things about triangulation and convex hulls and Voronoi diagrams and Delaunay diagrams and collision detection and shape approximation and fitting data to curves and surfaces. And Chris Bishop here in the math department works very hard on triangulations of provable quality with respect to angles. Vageli Koutsias attended my computational geometry course years ago when he first arrived. He studies computational geometry of proteins and molecules. It's everywhere. Of course, computational geometry is not new. It goes back millennia. We've been needing it to build our buildings, to navigate, to study the stars, to do everything in mathematics. Much of it is geometric. And my thesis is that computational geometry is everywhere. I can find computational geometry in every field represented in this room, I guarantee it. And it connects to everyday tasks. And that's what's really appealing to me about this area of algorithms. I got into it through route planning. Okay, I was with the Hughes AI Center. I was one of the inaugural first 12 scientists of a new field called AI in the AI Center at HRL. And the first robot I worked on was one of these little things called a terrapin turtle. And I assembled it and programmed it to move around and avoid obstacles. And I built things like this image that you see of a polygon with some obstacles, and you wanted to find a shortest path. And I had studied algorithms like Dijkstra's algorithm that Alan Tucker has in his book, how to find shortest paths. And I was learning the field of AI was expert systems and A-star search and things like that. And we were developing algorithms to do route planning, and that's what I became expert at. Piano movers problem, and my thesis at Stanford developed algorithms for finding shortest geodesic paths on surfaces and models that's used extensively in computer graphics. So roll the clock back 40 years, and my group was working with other universities. Carnegie Mellon and Stanford, ironically, my other two universities, were part of the team with Martin Marietta. And the first real large-scale successful development of driverless car technology, autonomous vehicle. It's called ALV, Autonomous Land Vehicle, a DARPA initiative even before the Grand Challenge and so on. And this big, huge vehicle, $2 million vehicle in 1984 dollars, was developed, and that little arrow points to me walking around it. I was in charge of building algorithms to do the planning, the route planning. And it was absolutely critical that I not just use heuristics, because they wanted to make sure this $2 million vehicle didn't bump into something. So you had to have guardrails on the algorithms, and I was giving them some provable methods. So my team is there, and we worked on building these models for navigation of this big autonomous vehicle. Fast forward to last summer, I had my first ride in a Waymo and navigated, and I was taking pictures and looking at the geometric model that was being built of my car, the cars around, the road, et cetera, because that's exactly what I was doing so many years ago. And this navigated me safely in Mountain View to my destination. So what's the role of algorithms now in the era of AI? So I work mostly in formal algorithms and analysis and things that can be provable, that come with guarantees. So we prove correctness and accuracy and the running time and approximation bounds and so on. It's very predictable. It's very transparent. You can tell people, here's the algorithm, here's how it works, and we can predict. And also, we don't need to have a ton of data to train a new algorithm if we're solving a new problem. AI, on the other hand, has this incredible black box power. It can learn complex, unstructured tasks. Now, it does have to be trained on a lot of data, okay? It is probabilistic, And there's challenges about how to explain the answers that it gives us. So a quintessential algorithm in my field, or a problem for which we seek algorithms, is the traveling salesman problem, the TSP. Okay, and you've probably heard about this. It's held up as one of the hard problems, very challenging problems. You have N cities, here they're in continental US, and you're a traveling salesperson and you want to find the shortest route to visit all of them or to do some errands, okay? And in what order should you visit them? And maybe you know that if you have N things, you can order them in N factorial ways. But of course, it's rather hopeless to write an algorithm that checks all of those orderings. So combinatorial optimization has developed lots of sophisticated techniques that allow us to solve bigger and bigger TSP problems. In fact, you can pretty much follow the evolution of the field of algorithms by how large of a TSP instance we can solve. So there's a lot of methods to work towards optimality. I work in areas of approximation, and I look at geometric versions of this. So what do I mean by a provable approximation algorithm? So look at how well your algorithm does, guaranteed on any input instance, and compare it to opt. And that ratio, if you can bound that ratio, then maybe you have an alpha approximation, where alpha is the largest that ratio can be. If, for instance, you're trying to minimize something like the length of a TSP tour. It's tempting to use greedy algorithms, where you try to take the best step in a myopic sense. What's the best step that I can take next? And greedy algorithms in the TSP setting will generally give you a logarithmic factor. Log is not constant. It grows slowly, but not too badly. But we teach in our courses simple algorithms that are within a factor 2 of opt. And for a long time, 1.5 times opt. So that's saying you can produce efficiently with a fast algorithm a way that gets you within 50% of opt. You know, opt might be 1, you produce 1.5. Can we do better than that? This has been lurking for decades and so on. Can we break the 1.5 barrier? And actually, it's still in review, I believe, but there is a very recent paper that does break the 1.5 barrier. Barely, you know, 36 nines there. But my interest has been, can you exploit special structure that might be there because of geometry? So for instance, this is one of my mottos. Without geometry, life is pointless. So look for the geometric structure in the problem. So TSP with geometric structure is something I've been interested in for a long time. Many of us have. In fact, my advisor, Papadimitriou, was the person who proved that TSP was hard even if it had geometric structure. So could you break the 1.5 barrier? And this was what we worked on. You could, in fact, get within 1 plus epsilon times opt for as small an epsilon as you wish. Epsilon's a favorite letter in mathematics. You can drive it towards 0. In fact, you can even develop provable methods that get you within 1 plus epsilon times opt in n log n time. That's as fast as you can sort n numbers. There's a caveat there. The constant grows exponentially, 2 to the 1 over epsilon. So we're not claiming these are practical. But these are algorithms that have guardrails, that we can say something provable about their performance, both in terms of optimal and in terms of the running time. And there's lots and lots of variants of this. The special structure that my particular algorithm exploited was what I call guillotine structure. And one of my students, as a parting gift, gave me this. If you come to my office, I have a guillotine on my desk in case you want to know why it's there. So one of the important variants of the TSP among hundreds that we've been looking at is TSP with neighborhoods. Esty and her colleague introduced this. You want to find a shortest route that visits a set of regions, whether they're disks or polygons or something like that. And for this, we and many others have provided provable algorithms. And another piece of work that we did together was with our postdoc Sándor Fekete on the lawnmower and milling problem. Find the best way to mow your lawn. And I mow my own lawn and I time myself, and I'm always looking for improvements. And one of our visitors last year from Shandor's group, Michael Perk, provided me with a provable optimal route to mow my lawn. He took the Google satellite image and provided that. This is a TSP problem. You have to get within the radius of your mower blade of every grass blade on your lawn. And the difference between lawn mowing and milling, lawn mowing, your lawnmower can go on the sidewalk. Milling, you have to stay inside the pocket. And that's where we work on pocket machining. So one of these practical projects that we did was with my postdoc Martin Held, who was here at Stony Brook and developed a lot of really great code. He's an expert on the computational geometry of pocket machining and optimal routes to mill or remove material. Now, there's the flip side of that, too. In computational geometry, we're very interested in additive manufacturing. How do you 3D print in an optimal way? That is, again, an optimal algorithm problem. Again, we have provable methods for this. You might want to sweep over domains carefully and optimally for many applications. The military is very interested for civilian search and rescue. MH370, how do you search perhaps under a prior distribution? Optimal search under uncertainty with an imperfect searcher, that's a topic of a proposal that we're putting together right now to look at these problems. Again, where we can provide provable approximation algorithms. Another variant is maybe you're removing material that's very relevant to the last week, a couple weeks here on Long Island, pick up material and move it. So I created this problem I called the snowblower problem. And the snowblower problem was very popular when I gave one of these freshman seminars. And one of the freshmen developed a game that you see there on the right, Rick Spillane, where you move the snowblower around, and when you dump the snow, it makes the nearby part of the snow higher. So you have to be careful when you use a snowblower. I was new to the snowblower. And so you don't want it to get higher than the opening size of your snowblower. Well, so my two-stage snowblower wasn't enough for a snowdrift that was 2 meters high. This is when we had about 1 meter of snow. Okay. Another thing that you're interested in the spirit of a TSP algorithm would be what we call the Watchman route problem, where you're trying to execute a route in order to see all of the domain, or to inspect a part, or to scan a model. There are companies involved in this problem too. A couple of my master's students developed a route to sort of fly around and see all windows of a simplified version of Manhattan. Guarding and coverage. There's a piece of paper coming around. I'm inherently a teacher, so you have some homework. There's a worksheet coming around asking you to find the fewest guards in a polygon. And I'm going to be handing out this worksheet at the Stony Brook School soon, where I'll be giving a lecture to high school students about computational geometry. And the guarding problem, you place a guard at this red dot, it illuminates this region. You want to place the fewest dots, the fewest guards, to see everything. That's the guarding problem. Maybe 5 guards is optimal. Maybe it's not. It's a really hard optimization problem. And we figured out ways to give guarantees. So another student in my undergraduate computational geometry class worked with me to develop heuristics, and we looked for both guard heuristics and witness point heuristics. And on the handout, you're to find both guards and witnesses. The fact that these 4 blue dots have non-overlapping visibility regions means that each of them needs its own guard. So even if you come up with an AI or heuristic-based algorithm to produce answers, you can do it, you can come up with a guarantee that you need at least 4. And maybe if you explore it with a heuristic to place guards, you can place only 4 guards. And then you'll know it's optimal. Okay? So this is an example where heuristics can provide some guarantees. In fact, at the Louvre, this showed up in the BBC, and I was teaching computational geometry to my undergrads last semester, and I said, oh, this is fantastic, I've got to bring this to the class. And this was they talk about exactly what we were doing in class, the art gallery problem, optimally placing guards. Alan mentioned that I've worked with NASA and the FAA on free flight and on air traffic management for quite a number of years. It's a multi-body motion planning problem where guarantees are vital, right? You want to make sure accidents don't happen. Planes do not get too close. And we were studying, among other things, impacts of weather. Weather is uncertain, so we took weather prediction models and developed algorithms for routing and estimating capacity of airspace. And it's very important to maintain the so-called RNP, the required navigation performance. That's the separation. In fact, focus in on the middle, that Time magazine article that you see there. I made it a little too small. This is paramount. Keep the aircraft at a safe distance apart. Otherwise, there's going to be disaster. We've also looked at load balancing, fairness. How do you decompose airspace into sectors so that air traffic controllers have comparable workloads? It reminds me a lot of political districting. And this is another place where algorithms come into play. One might think that this green region here shouldn't be one district. This is gerrymandering, right? So computational geometry and algorithms, we can study fair ways to partition according to certain constraints. And we can formalize the notion of what compact means, as is specified in the Constitution. Computational geometry is at the very foundations of AI and machine learning. When ChatGPT came out, my colleague Steve Wolfram came out with a freely available book, and the images he's using to describe neural networks and machine learning and unsupervised learning and clustering, he's got Voronoi diagram right there, and he discusses that as the basis of how machine learning works. Convergence of k-means algorithm was done by one of my former PhD students who won Test of Time Award for her work in this area. So what about provable algorithms versus AI? And I'm not going to draw a barrier between those two. I think there's roles for AI in algorithms, and there's a lot of roles for algorithms in AI. Okay, and you'll hear it mentioned that AI can be a so-called co-scientist, and that the formal analysis of algorithms can help us put guardrails on AI to make it more predictable in a sense. And here's a paper that came out just as I was starting to put this talk together. It came out within the last week. Accelerating Scientific Research with Gemini, Case Studies and Common Techniques. A large group of our colleagues in theoretical computer science, 151-page paper with lots of case studies. It was citing me. That's why I got an alert on Google to look at this when it appeared on arXiv. And amazingly, they have done several case studies of using AI to help solve provable algorithmic and theoretical computer science problems. Here's one of the conclusions that it draws in this multi-authored paper by Woodruff et al. This was using a proprietary version of Gemini in DeepThink that's still in development at Google, but soon it's going to be even better. And remarkably, there's case after case after case in this paper, the scientists involved in these problems use AI, and here you can actually see the 3 different prompts that led to a new theorem on a problem called robust core set design. I've worked on core sets, and I'm currently working on robust algorithms. And it actually closed the gap between the upper and lower bounds. So a well-advertised open problem. Its solution was developed by carefully prompting the AI, and it produced the LaTeX source to write the code, or to write the pseudocode for the algorithm and the proof of the theorem. Really remarkable. So, of course, they also point out the current limitations. There's confirmation bias. All of us that have used AI products know about the problem of hallucinations and this alignment friction that exists between the goals of the AI and the goals of the humans that are using it. So I created this meme. Full disclosure, it's an image generated by ChatGPT. I said, we stand on the shoulders of giants, right? And who's standing on the shoulders of all giants and all of us is AI. And where should we be standing? We should be utilizing AI to help us advance science. That's the core thing. And this prediction in their paper is the fundamental bottleneck of science will shift entirely from the generation of ideas to the verification of those ideas. And that's where we play a vital role, I believe. So a view to the future. We are in the century of the algorithm. We need to teach algorithmic thinking. Shout out to my colleague Steve Skeena, another person who helped us come to Stony Brook, who wrote the algorithm design manual that teaches you, you've got this kind of problem, here's the kind of algorithms to work on it. Of course, now maybe AI can replace an awful lot of that book. AI is a co-scientist in algorithms research. The biggest theory problem all of us worry about, well, not worry about, but would dream of solving is the P versus NP, Millennium Prize problem in the field. I won't go into what exactly that is. But the algorithm challenges that we all face as a field studying algorithms, we want to go beyond worst case analysis and average case analysis. We want to do algorithm engineering to figure out ways to exploit structure in the data, even if the mathematics doesn't say that we can always do this well. Let's do that well when we can, and let's discover it in the data. High dimensional data and tons of it, lots and lots of data. So the N is going way up, way beyond Moore's law. AI is an incredible black box. Can we help explain it? Can we do dynamic operations on data as we update? Accountability, there's all kinds of legal pitfalls for AI. Fairness and bias are incredibly important. Quantum secure cryptography, you're worried about quantum algorithms possibly getting us in trouble because my colleague Peter Shor came up with an algorithm for factoring numbers. Data privacy, sustainability, energy. So this is my closing slide. I'm really calling for algorithms. I want to hear your algorithmic problem. I want to hear what problem we might be able to help you model and solve. I've not found a field yet that doesn't have an algorithmic challenge where someone who studies algorithms and applied mathematics cannot help you with the model and hopefully also with the solution. So please feel free to reach out and contact me. I'm welcome to all of your problems. Thank you very much.
Thank you so much. Questions?
Joe, at the very end, you mentioned Peter Shor. Has more thought gone into your fields as how your algorithms would be modified or how you would modify them with the development of quantum computers?
That's a great question. So I'm not an expert in quantum computing. I work with people who work in quantum computing, and the question of provable algorithms in quantum computing is being pursued vigorously. Whether the hardware keeps up with it, I'm not sure. You're the physicist. You can tell me more whether we're going to achieve the necessary hardware. But meanwhile, the theoreticians are developing theoretical approaches with quantum computing. In some cases, they work well. My colleague Shandor Fekete did a study, though, on quantum computing in optimization, and it was quite disappointing what quantum algorithms could do. So I think the jury is still out. That's going to be a big part of the 21st century, quantum computing.
So my question is about information. At the bottom of everything we do is information. And in your case, it would be geometric information. People who do statistical processing, they have Fisher information. I'm sure there are efforts that to find canonical expression for geometric information. What is your opinion on it? Is it possible to find it, or it's something that will never happen?
That's a great question. So you want to be able to compute and evaluate the information content of a data set.
Yes.
The inherent, so We do in computational geometry look at the so-called inherent dimension of data. A lot of real data lies, while it might be in a million dimensions, it might actually live on lower dimensional manifolds. So that's one place where the data guides us in looking for the inherent dimension or perhaps the inherent information within the data. I think that's very important. That's an area that I'm not directly working in, but ultimately when we study these problems, we are looking at trying to extract the core information in a set of geometric data. Yeah.
Okay, so I'm a finance student, so this is going to be a fairly financy question. But do you encounter a lot of problems where the optimal may not be known? And specifically, if you're doing like a time-based problem where maybe the true optimal for a current period depends on the information in the next period, what is your approach to, I guess, creating algorithms or testing algorithms or running an optimization problem where, in the current period, you might not know the true optimal given the current set of information, but you're trying to figure out how strong your algorithm is across time without depending on this future bias.
Right. So, I mean, one thing that we tried to do is put bounds on it. So you may not know what the true opt is, but maybe you can put bounds. You can also try to compare it to, you can compare an online algorithm to an offline algorithm, and we speak about so-called competitive analysis. So an offline algorithm may know a lot more of the parameters specifying the problem, and you compare how an offline algorithm does in performance to the online algorithm. But ultimately, for the kinds of problems you're describing, I suspect it goes into the area of experimental algorithms, where we won't necessarily have a theory yet to explain how well we can do or what the worst case optimal algorithm is, but you experiment with it.
Thank you, Joe. What an inspiring talk. So since I'm from the same department, I definitely am very supportive. So I just want to make a comment. AI these days, basically most of the time we use a point estimator. The simplest AI models, they are also statistical models.
That's right.
And in statistics, a point estimator is not enough. You have to have something like a confidence interval. So that's the part we need to strengthen and to develop. And so, with Joe's leadership, we are really moving into that direction. We actually have this new graduate program in data science with core in machine learning. So we hope to also help everybody in the community to, with machine learning AI. Just a comment.
Absolutely, thank you. Yeah, uncertainty quantification. I think there was a question up here. Celia had her hand up. Uncertainty quantification and dealing with uncertain data, and what we may want to produce is not a single definitive solution, but a distribution of solutions and a set of confidence intervals associated with it. Yeah.
I wanted to ask you a question as a teacher, because we've heard about your teaching credentials, and it's so obvious from hearing you speak. And I'm so struck by that idea of AI as a co-scientist. And I wonder how you think about training the next generation of human scientists to be that without relying, or maybe they do rely heavily on AI from the beginning.
As we know, more and more students are relying on AI, sometimes against our academic integrity guidelines. But I think it's very important that we train them in responsible use of AI. And so I try to develop a dialogue with students and give them assignments that encourage them to try to use AI in problem solving. Sometimes I give them the solution that I get with a chat, and I ask them to critique it and look at it, because I really want them to be critical thinkers. Don't just accept AI as being correct. So that's where it said generation of ideas versus verification of ideas, and I really want to teach the students how to verify what they're seeing with AI. they're going to use AI. We want them to use AI. They're going to use it throughout their careers, and AI is at the infant stage right now. It's going to get far more sophisticated than anything that we see now. So it's critical that we teach our students how to use AI and how to use it responsibly.
Thank you so much. Can we give Dr. Mitchell another round of applause?
Thank you very much.